Hello, guys, and welcome to Aerominds Training Center. So, now we are starting with the Principles of Flight, Chapter 3. We have already completed Chapter 2 and Chapter 1, and I hope you like those videos. So, now we are going to start with aerodynamic theory, which says, which is based on something called the principle of continuity and Bernoulli's theorem and uh, aerofoil and lift concept, and also stream tubes and streamlines. So it's a very easy topic, but students do miss out things in this. So I'm going to explain this very slowly. And it's the principle of continuity name sounds very scary, but I promise you the idea behind it is actually very simple. And DGCL actually loves this principle because it is the base of the aerodynamics. And if you understand this properly, the wings lift, Bernoulli's theorem, Venturi effect, everything later will become very easy for you. Now I first want you to understand where this principle comes from. Okay, now it does not come from aviation, it comes from a very basic law of physics. Okay, it comes from physics, not from aviation. Okay, now the that law says that mass and energy can neither be created nor can be they destroyed. Okay, they can only change from one form to another. Now let me explain this in very simple words. Okay, now suppose you have 1 kilogram of air, 1 kilogram of air, and you cannot suddenly make it disappear. Okay, you cannot disappear it. You can also not magically create extra air from nothing. Okay, now that air can change its shape, its speed, its pressure, temperature, but the amount of air itself does not vanish and does not get created out of thin air. Okay, now this rule is true everywhere in physics, and aerodynamics also follows this rule very strictly. Okay, I hope you understand what I'm trying to say. Now we apply this basic idea, this very basic idea, to moving air. Okay, now to understand how the principle of continuity works in aerodynamics, imagine a tube. Okay, I want you all to imagine a tube. Now this tube is fixed. Okay, and the air is flowing through it. Okay, I want you to imagine that the tube is fixed and air is flowing through it, and the airflow is steady, meaning the flow is smooth, continuous, and it is not changing with time. Okay, no gusts, no sudden changes, just smooth flow. Smooth flow. Okay, smooth flow. Okay, now imagine that this tube is wide at the start, and then in the middle it becomes narrow. Okay, it thins, and then it again becomes wide. So the cross section area of the tube reduces in the middle. Okay, now I'll show you a diagram with which is going to help you in your imagination. Now imagine this, it's a tube. Okay, and in the middle somewhere the cross section area reduces. Okay, and the flow is smooth and steady. As I told you, it's smooth and steady. Okay, now I want you to think very carefully. Air entering the tube from one side and coming out of the other side. Okay, I hope you guys can see that. And air is not leaking out of the tube from anywhere, it is not leaking out, no leakage. Okay, now, air is not entering from outside, and whatever air enters must leave. So, whatever is entering, it is leaving. Okay, now comes an important question. If the tube becomes narrow in the middle, what should happen to the air there? Okay, now this is where the continuity comes into the picture, which is the equation of continuity, principle of continuity. Now, before answering that to you, we must understand something known as mass flow. Mass flow. Okay, now mass flow, what it means is, it simply means how much mass of air is passing through a particular point in 1 second. How much mass passing through a point. Got it? Now that is it for this. Nothing more complicated, and it is the mass of air which is per unit time. Now what things decide how much air is passing through in 1 second? Now first is the cross section area. This, okay, this is the cross section area. That means how wide the tube is. Cross section means how wide it is. A bigger area means more space for the air to pass, a smaller area means less space to pass. Got it? Now second is the velocity. First is the area, second is the velocity. Now The velocity means basically how fast the air is moving. Okay, faster air means more air is passing in 1 second, and slower air means less air is passing. And third is the density. The density means how heavy the air is. Okay, denser air means more mass in the same volume, and lighter air means less mass in the same volume. So mass flow depends on three things. Got it? First is your cross section area. Second is velocity. Third is your density. Okay, so three things. Got it? Now mathematically, how do we write this? It is cross section area, velocity, and air density. Area into velocity into density. Okay. Now, so you can imagine it like this. Area tells us how much space is available. Velocity will tell us how fast the air is moving, and density will tell us how heavy the air is. Okay. Now, for a steady airflow, and this is very important, the mass flow must remain constant. The mass for a steady airflow, the mass must remain constant. Now, if you ask why, because air is not getting created or not, it is getting destroyed inside the tube. So remember that. Okay. So if air enters the tube at a certain rate, the amount of air must pass every section of the tube every second. Okay, that means that area multiplied by velocity, multiplied by density gives you a constant. Okay, so this is called the equation of continuity. Okay, now listen carefully. DGCA may ask you directly what is the equation of what the equation of continuity is, but more importantly, they will test whether you understand what it means physically or not. Okay, now air is a compressible fluid. See this, air is a compressible fluid. Now this means that air can be compressed. Now if the pressure increases, density can increase, and if the pressure decreases, the density can decrease. Okay, so in general terms, the density can change. Density is variable. Okay, but here comes an important condition. At low subsonic speeds, which is now the low subsonic speeds means at less than 0.4 Mach, the density changes are very small. Okay, now these are so small that for the most practical calculations, we are ignoring them. We ignore them. Okay, so below now Mach 0.4 means 40% of the speed of sound. 40% of the speed of sound. Now most normal aircraft wings at normal conditions are operating in this region only, remember that. So below 0.4 Mach, we assume that the density is always constant. Now this thing is very important for your exam. If the density is constant, then the density can be removed from the continuity equation. If the density is constant, then it can be removed from the equation. So earlier we have area multiplied by velocity, which is multiplied by then density, which gives you constant. Now density is constant, so we are removing it. Now what remains is area multiplied by velocity equals constant. Got it? Now this is the simplified equation of continuity at low subsonic speeds. Now let us understand what this means in the real life. Okay. Uh, I hope you guys understand my teaching style, and so we'll move further then. Now let us understand what this means in our real lives. Okay, now if the area multiplied by the velocity is constant, if the area which is multiplied by the velocity is constant, then if the area increases or the area decreases, the velocity must change. So if the area decreases, velocity must increase. It has no choice. Now why? Because the product has to remain constant, it has to remain same. Okay, similarly, if the area increases, the velocity will decrease. Now this is the heart of the, you can call it heart of the continuity principle. Okay, now let me repeat it in a very simple way. So when the when the air flows through a narrow passage, when it flows through a narrow passage, what is happening to the cross section area? It is reducing. So the area reduces, the velocity will increase. Okay, and it happens in the same way. When the area is widening, the speed will slow down. This happens because the same amount of air is passed every second, because the equation is constant. Okay, now you can also imagine water flowing through a pipe. if you press the pipe and make it narrow, suppose you are watering your plants, or you are washing your car, if you are making it narrow, water comes out faster, and air behaves in the same way at low subsonic speeds. Now what happens if this rule is violated? If it is violated, what happens? Okay, if it does not work the way it is uh, saying. Now suppose velocity does not increase when the when the area decreases. Now then air would start piling up. Okay, but air cannot pile up infinitely, because mass cannot be created or not destroyed. So nature forces the velocity to increase only. Now this is not optional, it is compulsory. Physics will demand it. Okay, now DGC loves to test this concept in wings also. When air flows over a wing, the shape of the wing causes the airflow path to change. Airflow is like this, but when wings comes into that, the path of the airflow changes. Okay, suppose it was going like this, but when it came under the influence of the wing, it changes its shape. Got it? Now, what happens in some regions, the airflow passage becomes effectively narrow, like this. Okay, and according to the continuity, the velocity has to increase there, like this. Okay, so this is why the air is speeds up over the top surface of the wing, which is at low subsonic speeds, and at bottom it is comparatively less than the upper surface air. Now remember, the principle alone does not create lift. This continuity principle alone, it is not producing the lift, but it is one of the building blocks, you can say, that is helping in the velocity changes. Okay, now I want you to make one thing very clear, because most of the students are getting confused here. I have seen that the principle of continuity does not say why the pressure changes. Okay, it only tells us how the velocity changes, and that is due to the area changes, because the area is changing. Okay, now pressure comes later with Bernoulli's theorem. We'll study it in the next page. Continuity only talks about the mass conservation. Okay, only about the mass conservation. Got it? So if the question says low subsonic speeds, and so you immediately have to assume that density will be constant. And if density is constant, use the area times velocity equals constant formula. And so that means area increases, velocity decreases, constant. Velocity increases, area decreases, constant. Okay. Now also remember one more important thing. Uh, this principle is valid only for steady flow. Okay, it is only valid for steady flow only, and steady flow means the flow condition do not change with time, and the flow is and if the flow is unsteady, or it becomes turbulent by any chance, so then the simple form of this formula cannot be applied directly. Okay, now remember, if now DGC may ask you conceptual MCQs also for your PF exam. Now if they ask at low subsonic speeds, increase in the airflow velocity occurs due to the decrease in the cross section area. Okay, now this statement is true and comes directly from the continuity part. Okay, now they also may ask which principle explains increase in airflow velocity over the wing at low Mach numbers. Okay, the answer will be principle of continuity. Okay, so now we'll mark this. I think we have explained it more than enough. So remember this, one of the fundamental laws of physics is that mass can neither be created nor it can be destroyed, but can only change from one form to another. Got it? To understand how the principle of continuity applies to aerodynamics, consider a steady flow of air through a tube, and that has reduced cross section area in the middle, as I showed you in the picture. Okay, now we'll see the mass flow concept. So the mass flow rate, the mass of air which is passing through a point per unit time, depends on the cross section area, AVP. Remember this, velocity and density, rho. Got it? Now mass flow is A into V into rho, and for steady airflow it is equal to constant. Now this constant is known as the equation of continuity. Now we come to the application at low subsonic speeds. Now as we know, air is compressible, so the pressure changes can cause the density to also change. Now however, the changes in the density at speeds less than zero point 0.4 Mach are very small and can be neglected. Now, therefore, this equation simplifies to A into V is equal to constant. Got it? Now remember that velocity is inversely proportional to area. So if area decreases, velocity increases, and if area increases, then velocity decreases. Now comes the key conclusion of continuity. Because mass flow is must remain constant, any reduction in the cross section area causes the velocity of the uh, airflow to increase, or vice versa. Vice versa means opposite. Now if there is increase in the cross section, then the velocity will decrease. Got it? Now the principle this principle allows us to predict the changes in the airflow velocity around the shape, such as wings at less than zero point 0.4 Mach. So now we'll start with Bernoulli's theorem. I hope you guys have understood completely what is principle of continuity and what is the application of it. So now we'll start with Bernoulli's. Now it is the most one of the most important ideas in aerodynamics. Remember that always. Okay, most important ideas. And if you truly understand this, the lift concept, the drag concept, pitot pressure, airspeed indication, very everything will start making sense to you actually. Now if you try to mug this up, okay, without understanding, you'll always get confused. And so I want you just to sit and relax and watch this completely. So first we'll understand the statement, what it says. Now Bernoulli's theorem says that in a steady flow of an idle fluid, the in a steady flow of idle fluid, the sum of pressure energy and kinetic energy per unit volume remains constant. Got it? Now this sentence looks very heavy, so we'll break it down into very small pieces. Now, first is, what does a steady flow mean? As I told you earlier also, steady flow means that the flow does not change with time. Got it? Now, at a particular point, the pressure and the velocity are not jumping up and down every second. It is smooth and it is stable. Smooth and stable. Got it? So they are smooth and stable. Now Bernoulli's works only when the flow is steady. Remember this. It only works when it is steady. And if the flow is highly turbulent or it is changing rapidly, then this rule will simply not apply. Okay, properly. Now what is next? So next is the what is idle fluid. Now idle fluid, it is also very important for your exams. They can ask you what is idle fluid. So an idle fluid is basically a fluid which is incompressible and it does not have any viscosity. Idle fluid is, it is incompressible and it will have no viscosity. Remember this. Okay, now I'll explain both these words very simply. Now incompressible is basically means that density does not change. That is it. So, density does not change. Even if the pressure changes, the density will stay the same. Pressure changes, the density will stay the same. It will remain constant. Got it? Now in real life, air is compressible as we know, but at low subsonic speeds, which we have already studied earlier, density changes are very small. They are very small. So so for the Bernoulli's, at low speeds, we assume that air behaves like an incompressible fluid. Okay, now comes the viscosity. So I hope you got this. Now we'll come to the viscosity part. Now viscosity means the internal friction, actually the friction of the fluid. Now honey has high viscosity. I hope you guys can imagine it. Water has low viscosity. Honey has high viscosity. Air also has viscosity, but for the basic Bernoulli's explanation, we assume that the viscosity for air is zero. That means no energy is lost due to the friction. Okay, so when we say idle fluid, we are actually making life easy for us, for ourselves. Okay, now DGCA knows this is an knows that it is an assumption, but you must also know that this is an assumption. Okay, now let us understand the core idea of this Bernoulli's theorem. Now Bernoulli's says that the energy does not disappear. Okay, it only changes the form. Only changes the form. It only changes the form. Remember this. Now in a flowing air, energy exists mainly in two forms. Only two forms. Energy is existing in two main things. So first will be the pressure energy, and second will be your kinetic energy. kinetic energy and your pressure energy. Okay. Now pressure energy is related to your static pressure. Static pressure, we have already studied it, height of the column above us. So pressure energy is related to your static pressure, and static pressure is the pressure exerted equally in all the directions when it is moving smoothly. Okay, I hope you guys remember that. Then kinetic energy is related to the motion. Now faster air has more kinetic energy, slower air has less kinetic energy. That also I hope you guys understand. Now, Bernoulli says that if you take a unit volume of air, suppose you take a unit volume of air, which means basically a fixed amount of air, okay, and you add its pressure energy and its kinetic energy. If you're adding its pressure energy and its kinetic energy, uh, the total remains constant as long as the flow is steady and the fluid is idle. Okay, that is it for this. So if one of it increases, the other must decrease. Pressure energy plus kinetic energy is equal to constant. Now if one is increasing, other have to decrease. If one is increasing, the other has to decrease. Got it? Now let us write the mathematical form, but do not panic. I'll explain this slowly. Now static pressure plus the kinetic energy per unit volume is equal to constant. Now this is written as P plus half rho V square is equal to constant. Got it? Now what do these symbols mean? So P is the static pressure. It is the pressure that pushes on the walls, on your skin, on your aircraft surface, etc., etc. Then comes the rho, which looks like a curly P, like this. It is the density. Okay, air density. V is the velocity of the airflow. Half rho V square is also known as dynamic pressure. Remember this. Okay, so dynamic pressure is the pressure which is due to the motion of air. Motion of the air. So it is corresponding to the kinetic energy only. Okay, so it simply means, so the this complete equation, it simply means that the static pressure plus the dynamic pressure is equal to constant. Now DGC expects you to know this relation very clearly, and now I'll explain the dynamic pressure in simple words. So if air is not moving, the velocity is zero, so dynamic pressure will be zero. Remember this. Okay, half rho V square it is. So if this is 0 square, everything is multiplied in this, everything will become 0. So dynamic pressure will be 0. And since the total pressure must remain constant, the static pressure must decrease. So if the dynamic pressure is 0, then all we are left with is static pressure. So static pressure is equal to constant. Now if the air starts moving faster, the velocity will increase. So the dynamic pressure will increase. But since the total pressure must remain constant, then the static pressure has to decrease then. Got it? So faster air means lower static pressure and slower air means higher static pressure. That is it. So this is the most tested idea in Bernoulli's theorem. Uh, so now we'll move through a given example, a numerical example, and static pressure is given as 101325 Newton per meter square. Density is the ISA sea level density, which is 1.225 kilogram per meter cube. Velocity is 52 meters per second, which is equal to 100 knots. Now we calculate the dynamic pressure. So dynamic pressure is half rho V squared. So half multiplied by 1.225 multiplied by 52 squared. Now when you calculate this, you get approximately 1656 Newton per meter square. Okay, so total pressure will be equal to this plus this. Okay, static pressure plus dynamic pressure. Now we'll get 102981 Newton per meter square. Okay, now if you ask why is this important? Now it is because the total pressure remains constant along a streamline in ideal conditions. Okay, now we'll mark this. So Bernoulli's theorem states that in a steady flow of an ideal fluid, the sum of the pressure energy and the kinetic energy per unit volume remains constant. Now, an ideal fluid is incompressible and it has no viscosity. Remember this. Now comes the mathematical form. So the static pressure plus the kinetic energy per unit volume is equal to constant. Remember this. Got it? Now static plus dynamic is equal to constant, where P is the static pressure, half rho V square is the dynamic pressure. Now we saw an example, and now we'll move to the what happens when the velocity changes. effect of the velocity change. Now, if the airflow velocity increases, if this velocity is increasing, the dynamic pressure will also increase. Now, if the velocity is decreasing, the dynamic pressure will decrease. So, if the dynamic pressure is increasing, remember this, if it is increasing, the static pressure will decrease to maintain the constant. Got it? To keep the total pressure constant. So, remember this, if one increases, the other has to decrease to maintain the constant. And this is basically Bernoulli's in action. So this is what it means. So if the airflow velocity doubles, the dynamic pressure will increase by 4 times. Remember this also. Okay. And the static pressure decreases to maintain the constant. So important result is that static plus dynamic is equal to constant, and this constant is also known as total pressure, stagnation pressure, or pitot pressure. Got it? Now, now I want you to understand a very basic, simple mental picture. Okay, imagine you have a fixed total energy. Okay, you have a fixed total energy. Okay, now you can store it either as pressure energy or as motion energy, which means that as potential energy or as kinetic energy. Now if the motion energy increases, the pressure energy has to reduce, and if the motion energy reduces, the pressure energy has to increase. Now you can see that DGCA is having three different names for the same thing. Okay, but remember that the all three mean the same thing in the Bernoulli's context. Okay, and remember that the stagnation pressure means the pressure when airflow is brought to rest smoothly without loss of any energy. Okay, now because this is exactly what is happening in the pitot tube also. Okay, now this is extremely important for your airspeed indicator understanding later. Pitot pressure. You will study about this potential plus kinetic is equal to constant. You will study it in your instruments navigation. Got it? So now we are going to connect Bernoulli's with the shape of the aerofoil. Okay, because Bernoulli's theorem does not say that velocity changes automatically. Velocity changes because of the shape and the continuity. Because of the shape and the continuity. Okay. Now, if the airflow passes over a curved aerofoil or through a narrow region, the velocity changes due to the continuity. And once the velocity changes, the Bernoulli tells us what happens to the pressure. Okay, so continuity explains the velocity change, and Bernoulli explains the pressure change, which is due to the velocity change. So we can see this in the diagram. The pressure changes, the velocity changes. Pressure changes, velocity changes. Now, in case of an aerofoil, so this shape is an aerofoil shape. At the top, we have the low pressure. Down, we have the high pressure. Now, as the normal pressure increases, the velocity will decrease. As the pressure decreases, velocity will increase. Okay. Now let us go through the uh, key ideas again slowly. Okay, so because repetition will build you great learning, so that is why I focus more on repeating things one by one. Now, airflow velocity depends upon the shape of the object over which it flows. Okay, which means that when the velocity increases, there will be a decrease in the static pressure. Static pressure will decrease. When the velocity decreases, the static pressure will increase. Got it? Now, this happens because the total pressure remains constant in a steady flow of the idle fluid actually. Okay. Now, what happens if the Bernoulli's theorems are not met? If you think about that. So, if the flow is not steady, or if the viscosity losses are very high, or you can say if the compressibility effects are stronger, then the Bernoulli's will not give accurate results. Okay, and this is why high Mach numbers corrections are required. Okay, but for your DGCA CPL level technical general exam and the low subsonic speeds, Bernoulli is perfectly valid conceptually. Okay, now, if we come to the exam logic, how is this asked in the exam? Now, they may ask increase in airflow velocity causes what change in the static pressure? So, you have to say that the static pressure will decrease. And they may ask if the pitot pressure consists of which two components? Then you'll ask static pressure plus dynamic pressure. Static plus dynamic pressure. Got it? Now, if they ask which theorem explains pressure drop due to increase in the airflow velocity, so you will say the Bernoulli's theorem. Got it? So remember this: airflow velocity depends upon the shape of the object over which it flows, and increase in the velocity decreases the pressure, decrease in the velocity increases the pressure. Got it? So remember, for the one last time, air is having some energy, and some energy is because it is moving, and some energy is because it is pressing. That is it. So moving is due to dynamic pressure, and pressing is the static pressure. Okay, and the total energy will remain the same. And the faster the air moves, the it presses lesser, and the air moves. If the air moves slower, it will press more. So up to now, we have used tubes, we have used narrow passages, everything, the basic simple flow examples. Now, those were only to help your brain understand continuity and Bernoulli's. Okay. Now, I want you to make one thing very clear from the beginning, because DGCA students often get confused here. Okay. Now, those tubes are not helping you to fly as an airplane. Okay, now an airplane does not fly because the air is passing through a pipe or a venturi. The tube examples were only for the illustrations. Okay, they were only the teaching tools, if you ask. Now they helped us understand how the air behaves when the space changes. Okay, and when the speed changes. That is it. But an aircraft does not have a tube on the top of it that sucks air. Okay, so now we move to the from the theory examples to the real flying object actually. Now to generate the lift, we use a specially shaped body kind of thing, and that body is known as aerofoil. Okay, it is called aerofoil. Now to generate the lift, now let me repeat this slowly. An aerofoil is actually a specially shaped object. I've told you, specially shaped body which is designed to produce lift, and it produces lift with relatively high efficiency as compared to other body parts. Okay, now the wings, tail planes, propeller blades, helicopter blades, all these are actually aerofoils only. Okay, now why do we need a special shape, if you ask? Okay, why not a flat plate is working? Because the shape is controlling the airflow, as we studied in the Bernoulli's. The shape is twisting the velocity, it is twisting the pressure. So the airflow behavior decides the velocity, decides the pressure, and the velocity and the pressure decide the lift. Okay, so they are interrelated. Now if we understand the lift generation on a aerofoil step by step with patience, we'll go like this. So when air flows towards an aerofoil, what happens? Suppose this is an aerofoil, the air splits into two parts. One goes here and one goes here. Okay, now some air goes over the upper part. We'll see in the diagram now. Some goes over the upper part, some goes over the lower part. Okay, now due to the shape of the aerofoil, the airflow over the upper part is made to move faster. On the upper part, the air moves faster. You can see the velocity has increased. Now, at the same time, the airflow which is below the aerofoil moves slower as compared to the top. Okay, I have already told you this. So the upper surface, now I want you to not just blindly memorize this just because I've told you. Now I'm going to explain properly why this happens. Now what happens, the upper surface of an aerofoil is usually curved. As we can see, it is curved as compared to this, more curved. Okay, now this curvature actually causes the streamlines to come closer. These are streamlines, we can see air streamlines. These are closer here and not so closer there. Now, when the streamlines are coming closer, what happens? The space reduces. Okay. Now, from the continuity, when space reduces, what happened? When the area reduces, the velocity increased. Remember this. We already know this. So, area reduces, velocity will increase. Got it? Now, below the aerofoil, the streamlines are not usually are usually farther apart. Okay, so more space is available. So velocity remains lower there. Okay. Now, once the velocity is changing, once the velocity changes, the Bernoulli's theorem also comes into the play. Now, faster airflow on the upper surface means that lower static pressure on the upper surface, lower pressure, faster airflow, lower pressure. Okay, and now this pressure is a pushing force. Remember this, it is a pushing force. So higher pressure below pushes the aerofoil upward. This is the aerofoil. This is the aerofoil. This is the low pressure, high pressure here. Okay. Now this is the pushing force which is pushing the aerofoil from beneath. Okay. So the lower pressure above pulls less downward, and this upward force, and there will be a net force which is the resultant, and the resultant force will be called lift. Okay, so the lift is nothing but the pressure difference between the low pressure and the high pressure, because the air from the high pressure tries to move to the low pressure, high to low. Okay, so it tries to move upwards, and which in return generates the lift of the aircraft. Okay, so it is not, the lift is nothing but the pressure difference only. Okay, it is not the lift is not just generated by the speed. Lift is created by the pressure difference. The main word here is pressure difference. Okay, uh, and speed difference is caused by the speed difference is causes the pressure difference, and but the pressure difference will create the lift. So remember, speed causes the pressure to differentiate, and the pressure difference creates the lift. Okay, now the next we'll see. Now the next line says that a larger surface area produces greater lifting force. Okay, larger surface area, greater lifting force. Now what happens if you see about a simple logic? Now pressure acts over an area. Now if you have more area, the same pressure differences produce the more force. Okay, this is why the big aircrafts like 3 A380s or 747s, they have high heavy and big wings. Okay, but which is so that they can create lift for that heavy aircraft. Okay, and small wings lift less weight unless the speed is very high. That is why the small aircrafts like Cessna 172s or 52s have a smaller wing. Okay, now remember one very important point, that the airflow over a aerofoil behaves very similarly to airflow through a converging or a diverging tube. Okay, so remember it is an analogy, not a literal tube. Okay, now the shape of the aerofoil creates regions where the stream tubes narrow and widens. So we can see this. This is converging, this is diverging. Okay, so we can see like this is called converging, this is called diverging. Okay, so in this, the shape of the aerofoil is creating regions, so the continuity will still apply. Okay, Bernoulli's theorem will still apply, continuity will still apply, Bernoulli's will still apply. So we are not breaking any rules of the physics, and so we'll mark this first and then move forward. So the tubes discussed earlier are only illustrations to explain the continuity and the Bernoulli's theorem, and they do not directly make an aeroplane fly. Okay, now if you want to generate lift, we use a specially shaped body which is called an aerofoil. Okay, now lift generation on an aerofoil. Aerofoil over the upper surface travels faster, airflow, and airflow below the aerofoil travels slower. This creates the pressure difference, which results in the force that acts upwards. And I've explained this very clearly. Now, larger surface area causes greater lifting force, and the airflow over the aerofoil behaves very similar to the airflow through a converging diverging tube. So, the continuity and the Bernoulli's theorem both will apply. Got it? Now we move to something very extremely important, which is the streamlines and the stream tubes. It is the last topic for this chapter, because it's a very small chapter. We'll probably complete it in one part only. Now we'll see what are streamlines. Okay, now a streamline is the path which is traced by a particle of air in steady airflow. Streamline is the path which is traced. It is the path, remember this, it is a path. Okay, now that means if you imagine a tiny air particle, suppose this, and wherever it goes, the line it follows is a streamline. Suppose it is going like this. So this is a streamline. Anything you can do it. Okay. Now it will not be random. It will always be a steady flow. Now streamlines are smooth and well defined. Always remember, they are smooth and well defined like this. Okay. Now, as I've told you, these are not random. Then comes the key properties. So uh, first is streamlines cannot cross each other. Okay, each of these three matter. Remember, streamlines do not cross each other. Why? Because if two streamlines are crossing, it would mean that air particle has two different velocities and directions at the same time. Okay, which would not make sense. That is impossible. So one point cannot have two different flow directions at the same time. So if you ever see a diagram with crossing streamlines, it is wrong. Remember that. Now DGCA can ask that conceptually. Now comes the closely spaced streamlines indicate high velocity. Closely spaced streamlines means high velocity. Streamlines cannot cross each other, and widely spaced streamlines mean low velocity. Remember this also. Okay. Now, why is this so? Closely spaced streamlines means high velocity because the closer the streamlines will be, means the less the space of the air will be there. Okay. Now, less space means that higher velocity, and here the principle of continuity is applying. Okay. Area is decreasing, velocity is increasing. Okay. Now comes the now widely spaced streamlines indicate low velocity. More space means they are slower flow. There's the slower flow. Got it? Now comes the effect of the streamline behavior. Effects. Okay. So first is the converging streamlines. Now when the flow accelerates, okay, flow accelerates. Now when the streamlines are converging, when they converge like this, as we saw here, when the streamlines are converging, they mean that they're coming close together, the flow will accelerate, the velocity will increase. Okay, and when these velocities increases, the static pressure decreases. Now comes the Bernoulli's here. Okay, so converging streamlines mean accelerating flow and decreasing the pressure because the area is decreasing. Okay, now when the streamlines are diverging, the area is increasing, so the speed will reduce and the pressure will increase. Okay, so now we'll mark this. The effect converging streamlines means accelerating flow and decreasing pressure, and diverging streamlines means decreasing flow and increasing pressure. Got it? So now we'll move to the stream tube concept. Now, stream tube is actually an imaginary tube which is formed by a bundle of streamlines. Okay, it is a many streamlines are there in the stream tube. Now, imagine many streamlines are together, forming it like a tube-like structure, and that thing is called a stream tube. So I'll show you the image. Now, these are the streamlines, the purple ones, and the red shape is called a stream tube. So this is a stream tube. Okay, now comes the important properties. So no airflow crosses the walls of the tube. Now why? Because the walls themselves are the streamlines. Okay, and streamlines do not cross each other, so basically like that. Now air flows only along the tube. Air flows only along the tube. That means that air enters from one end and leaves from the other. Okay, no mass flow inside the steam tube remains constant. Mass flow now the mass flow remains inside remains constant. Okay, why? Because no air enters from outside or no air leaves sideways, so whatever mass is entering, that mass will be leaving. Okay, now again the continuity concept is there. Okay, now if you ask why do we study the stream tube concept, so basically they help us visualize the airflow around a aerofoil. Okay, now instead of thinking air is flowing in an open space or anywhere else, we imagine that invisible tubes are formed by streamlines. Okay, now when the stream tubes narrows, the velocity increases, and where the stream tube widens, the velocity decreases. So even around a wing also, the airflow behaves as if it is flowing inside a tube made of streamlines. Okay, now this kind of mental picture is very important for your own knowledge. Okay, so a steam tube is an imaginary tube which is formed by streamlines. No airflow crosses the walls. Air flows only along the tube. Mass flow inside remains constant, and this concept helps us visualize airflow around an aerofoil as it if were flowing inside a tube which is made up of streamlines. Got it? Now DGCA does not expect you to does not expect any fancy mathematics here. They expect correct physical understanding only. Okay, now if we connect everything, so we have completed what is equation of continuity, we have done what is Bernoulli's theorem, and then we have seen what is the mathematical form, then the key takeovers and aerofoil concept, streamlined concept, and everything. So now we'll move to the MCQs. So these are all the MCQs according to which we have studied now. There are around 30 MCQs. So that is it for this chapter. Now we have completed this chapter. I hope you guys understood it. And if you have any doubt, you guys can comment down in the section, in the comment section, and your doubt will be resolved. So that is it for this. I'll see you in the next one. Thank you guys and take care.